Susana Enomoto. I'm a PhD student in computational modeling at Rio de Janeiro State University. My advisors are Professor Vasquez from the Ohio State University and Professor Alves Filho from Rio de Janeiro State University. Today I would like to present a general idea of my PhD project, which is about computational modeling of neutral particle non-classical transport in energy multigroup diffusion formulation. Here's the overview of this presentation. First I will present motivations and goal of this project. Secondly, I will present the mathematical modeling I'm applying in this project. In section 3, I will present the results I have obtained so far. In section 4, I will present a general timeline of the PhD course and the specific timeline of this semester here at OSU. And in the last section, I will present acknowledgement. I will start the motivation section talking about some applications of the non-classical neutral particle transport theory. Some of the applications are photon transport in atmospheric clouds and neutron transport in pebble bed and boiling water nuclear reactors. Since 1997, Rio de Janeiro State University's Deterministic Computational Neutronics (DCN) research team has been working on classical neutral particle transport computational simulations. These simulations are applied on nuclear reactor physics and radiation shielding. Our team has made significant contributions in the numerical solution of neutral Boltzmann linear transport equation and diffusion equation in coarse spatial discretization grids. The CapesPrint program offers the opportunity for the DCN to also make contributions in the area of non-classical transport with the Nuclear Engineering Graduate Program at OSU, with joint publications of the results in specialized journals, and the internationalization of the graduate program in computational modeling and building concrete collaborations with more experienced researchers in the neutral particle non-classical transport are some of the goals of this project. Now I'm going to present the mathematical modeling we are considering here. We have the non-classical transport equation and the classical transport equation. Both equations are balance equations where the left-hand side represents the removal of particles and the right-hand side represents the production of particles. Psi is the angular flux, sigma t is the macroscopic cross-section, delta is a delta function, c is a scattering ratio, and q is an internal source. In the non-classical transport, the distance between collisions, that is S, is a variable of the problem, and macroscopic cross-section depends on S and P of S, which is a distribution function. And in non-classical transport, the centers of scattering are correlated, and in classical they are uncorrelated. Now I'm going to talk about the diffusion theory. The diffusion theory is based on Fick's law, which states that particles migrate from points of higher concentration to points of lower concentration. It is an approximation of transport theory that can provide great numerical results. Here we have the classical monoenergetic diffusion equation and the non-classical monoenergetic diffusion equation. In the non-classical, we have the variables given by equations 6 and 7 that are the mean free path and the squared mean free path. They are also balanced equations, where the left-hand side represents the removal of particles and the right-hand side represents the production of particles. Now I'm going to talk about my original contributions in the field. I have developed this equation, the non-classical multigroup diffusion equation, and I have developed and implemented the analytical non-classical multigroup diffusion method. And I'm working on benchmarks to validate this new formulation. Here we have the classical multigroup diffusion equation and the non-classical multigroup diffusion equation. They are balanced equations. They are in three-dimensional form, and the difference is that in non-classical we have the dependence of mean free path and squared mean free path. Now I'm going to show some results obtained by this new formulation. These are the parameters of the problem. We have a problem with two groups of energy, macroscopic cross-section of each group, and internal source of each group, and the scattering matrix. The boundary conditions is vacuum, and it's a slab of 10 centimeters. And the P of S is given by this explanation. In the first graph, we have the results obtained by the analytical non-classical multigroup diffusion method, and the second graph represents the results obtained by the non-classical multigroup Monte Carlo method. Both solutions are similar. The Monte Carlo method solution was generated with 50,000 particles, and we are going to perform simulations with more particles to obtain a better benchmark. Now we have another results with same parameters except for P of S. This P of S is non-exponential, and it's a P of S of simplified P2. The second graph represents the results given by the analytical diffusion multigroup method, and the second given by the non-classical multigroup Monte Carlo method. We can see that the results are different from the previous one because P of S here is non-exponential. So the results given by the classical diffusion analytical multigroup method is different from these results here. Here's the PhD timeline given by year and semesters. I have completed all the subjects and exams, and now I'm working on my PhD project here at OSU, supervised by Professor Vasquez, and developing computational codes. Then I'm going to perform numerical results and elaborate my dissertation. Here's the specific timeline of this semester here at OSU. I have completed the computational implementation of non-classical multigroup diffusion method, and now I'm working on numerical validation of this new formulation. And I'm going to formalize the work realized here. I would like to thank CAPES by the financial support, and I would like to thank my advisors, Professor Vasquez, Professor Filho, and Professor Barros, for all the support. This work would not have been possible without their support. Thank you for your attention.